Hello everyone, I hope I find you doing well. I'm Renzo and welcome to RUAT's Aerodynamics workshop. So in this workshop I'll be walking you through some basic aerodynamic concepts to help you in your designing of your glider for this year's RUAT glider competition. Alright, let's get started. So here's an overview of the topics that we will be covering in this workshop. The first section is airfoil aerodynamics, and it'll be talking about what's an airfoil, how do they generate lift, what are wing lift curves, the importance of aerodynamic center, and the characteristics of an airfoil in terms of their aerodynamics. The next section is going to be all about airfoil geometry, and it'll be talking about the different geometric parameters of an airfoil, as well as some examples of airfoils that are used in free flight competitions. And the last section will be talking about the geometry of the wing and the tail, and the terms that you need to understand, as well as what aspect ratio is, taper ratio, dihedral, and in tail geometry we'll just be talking about the functions of the tail as well as different arrangements of tail. Alright, so what is an airfoil? Well, basically it's the heart of the aircraft and affects many of its characteristics in terms of flight, such as speed, takeoff and landing distances, stall speed, handling qualities, as well as aerodynamic efficiency. And over here on the right we have some examples of airfoils, and they're basically just the cross section of a wing. So here you have some examples of typical airfoils for aircraft, as well as an airfoil for a propeller blade. Here there's an example of, a couple examples of natural airfoils used in nature. So here's the wing of a blackbird, here's the wing of a dragonfly, and the flipper of a dolphin. And here's some more additional examples of airfoils for different applications. You can see here there's one for a sailboat, and they all do pretty much the same thing. They manipulate the flow of air so that they can generate some sort of force. It doesn't have to be an aerodynamic force. Here we're using an example of a dolphin flipper. Obviously it doesn't use air, but it does the same, it follows the same principles in terms of fluid mechanics, where it produces a force based on the flow of some sort of medium fluid. So an airfoil generates lift by changing the velocity of the air passing over and under itself. And the airfoil's angle of attack and/or camber, which means curvature, causes the air over the top to travel faster than the air traveling underneath the airfoil. And the angle of attack, which is usually denoted by the Greek letter alpha, refers to the angle of the airfoil's chord line with respect to the flight path. And now the airfoil's chord line is just the distance between the leading edge and the trailing edge, and the flight path is just the direction of the flow of air upstream from the airfoil. Now, from Bernoulli's principle, it states that Higher velocity air produces lower pressures, and lower velocity air causes higher pressures. And the diagram over here on the right better illustrates that concept. As you can see here, the upper surface of the airfoil causes lower than ambient pressures because of the faster traveling air. And the direction of the arrow shows the tendency to which the airfoil will drift because of that difference in pressure. And it also represents, in terms of vectors, lower than atmospheric pressure. So you can see here at the top surface, there's a large area where the air is below atmospheric pressure because of the way the air is traveling above the surface of the airfoil here. So based on Bernoulli's principle, the air must be traveling faster here than the flow of air in the surrounding of the airfoil. Here you can see that the pressure is above atmospheric because the airflow is coming to a stop here at the blunt surface of the airfoil. And now as the air travels underneath the airfoil, according to this diagram, I suppose the air is traveling faster than ambient pressure here in this region, because you can see that the arrows are moving away from the surface of the airfoil. And here at this point, the airflow is slower than the ambient flow. So that's why, as with here, the region has above ambient pressure. Now, if you were to take all these vectors, you can see that most of the lift, excuse me, is produced by the upper surface. And you can also see that there's a net pitching moment causing the airfoil to pitch downwards because of the way the airflow is flowing along the surfaces of the airfoil. So so the takeaway from that is that there's a pitching moment here caused by the aerodynamics, as you can see from these arrows. And if there was to be any damage to the airfoil, the most critical area would be the upper surface, because that is where most of the lift is generated by the airfoil. And in fact, typically it's about 2/3 of the lift. So that's why it's very critical that this surface here remains undamaged. Now, there are a lot of misconceptions when it comes to the generation of lift due to an airfoil, and one of them is that the length of the upper surface of an airfoil here actually has no effect on the speed at which the air travels. Okay? That's an incorrect assumption associated with the longer path or equal transit time theory. And if you were to have a symmetric airfoil, which is very common, that would mean that that airfoil wouldn't produce any lift, because the upper surface and the lower surface would have the same distance. So the main takeaway is that it's not the distance that causes the difference in pressure. It's the angle of attack or the camber, which is just, it has the same effect as changing the angle of attack, the camber of an airfoil. And yeah, now there are lots of ways to interpret how lift is generated by an airfoil. As you can see in this diagram to the left, there's the Newton interpretation, which states that lift on an airplane wing can be considered to be the Newton's third law reaction force to the downward force on the air. And then there's the Bernoulli interpretation, which I explained earlier, that states that the lift on an airplane wing must be consistent with the Bernoulli equation, since it is an expression of conservation of energy in the fluid. Now, you don't have to understand what that, you don't have to internalize what this means, but my previous explanation on the pressure differences and the flow of air is the summary of the Bernoulli interpretation of how lift is generated by an airfoil. Okay, so I just explained that the angle of attack of an airfoil and or its camber is the main reason why an airfoil is able to produce lift, and it does that by changing the flow of air around the airfoil. Now, the variation of lift with respect to the angle of attack of an airfoil is linear, as you can see on this plot here. And by the way, this plot is referred to as a lift curve plot. So as long as the air remains attached, the lift will increase linearly as you increase the angle of attack of an airfoil. Now, different shapes of airfoils have their own characteristic lift curve plots. So depending on their shape, this region where it's attached, it's still going to be linear, but they're going to be of a different slope. Well, later I'll show you a bunch of variations on the lift curve slope. And in addition to the lift curve slope, airfoils have their own characteristic plots for their drag characteristics and their pitching moment characteristics. And again, I explained in the previous slide how the pitching moment is generated by the airfoil, and that's also an important plot to know in terms of the characteristics of your airfoil. But for now, we're just going to focus on the lift. And as you can see, the variation isn't always linear. As you increase your angle of attack, the flow will actually begin to separate, as you can see here in this diagram. And on the lift curves plot, it's represented by this region that's nonlinear, and it's called the stall region. And that represents the part or the occurrence of flow separation because your angle of attack is too high. And when stall occurs, there is a loss of lift, as you can see here, as well as a large increase in drag. And that's because here, as your flow separates, the region of air here underneath the wing or airfoil is of a much higher temperature, and then here, higher pressure, and over here there's going to be a lower pressure, so there's going to be a net pressure drag. That's what they refer it to, that is caused by the flow separation. Now, flow separation is an important concept to understand in aerodynamics. Again, we go back to this diagram and a flat board here that has no curvature, aka camber, at an angle to an oncoming flow of air will produce lift. But if you increase its angle of attack high enough, it'll easily separate the flow of air around it. So the flow of air is no longer attached, and that's what you call the stall condition. And again, flow separation causes a disturbance in the airflow, resulting in a reduction in lift and a large increase in pressure drag. And here, you'll start to appreciate the importance of camber or curvature. So curving the airfoil, aka adding a camber, delays the occurrence of flow separation, resulting in an increase in allowable lift and drag because the stall hasn't occurred at that angle of attack. And if it isn't evident, you can see that both plates are actually at the same angle of attack, but because this one has a camber, flow separation hasn't occurred yet. An airfoil with camber will produce lift even at zero angle of attack. So here, let's pretend that the lift curve of this cambered plate is this curve here. Because it's cambered, at a zero angle of attack, it actually produces lift. And it will take you to have the angle of attack being negative for it to produce zero lift, right? So for cambered airfoils, the angle of attack needs to be negative to produce zero lift. And I suppose the effect of having a camber on an airfoil versus having no camber is essentially just shifting the curve upward, right? So if the lift curve for this plate were to be shown, it would probably look like this. And because it's symmetric, and of course this region here is the stall region. All right, again, so this diagram shows the effect of camber as well as aspect ratio, and we'll talk about aspect ratio later. This is more relevant to 3D wings. Right now we're just talking about the cross section of a wing. So here you can see more clearly that adding a camber on a wing or an airfoil will shift the curve upward from the original uncambered plot. And again, uncambered means symmetrical, and symmetrical airfoils have curves that have their origin at that generate lift, zero lift at zero angle of attack. So here we summarize the aerodynamics of an airfoil. So the interactions of airflow and the aircraft, such as friction and pressure, are the reasons why we get aerodynamic loads, just like lift. And in addition to lift, an airfoil will aerodynamically produce drag and pitching moments. And earlier I've explained the generation of pitching moments again with the pressure distribution along the airfoil surfaces. And I kind of touched on how drag is produced from flow separation. And of course, the more typical version of drag that most people think of is friction. And then that's caused by the interaction of the airflow on the surface of the aircraft. So that's there too. Now, by definition, the lift is always perpendicular to the flight path. So that, again, flight path is the direction of airflow upstream from the airfoil. And the drag, which is an opposing force, is always parallel to the flight path. So drag is always seen as a force that hinders the motion of an aircraft. And airfoils with a positive camber will produce a negative aerodynamic pitching moment, nose down direction. So that again is my earlier explanation of the pitching moments due to the pressure distribution. And symmetric airfoils will produce no aerodynamic pitching moment, and that's because the upper surface of the wing and the lower surface of the wing will have the same pressure distribution, and the way that the pressure is distributed on the surface is going to cancel them out. So there's no aerodynamic pitching moment at zero angle of attack, because the way the flow is moving above and below is the same. And I guess at that angle too, there wouldn't be any lift caused. Okay, so what is aerodynamic center? Aerodynamic interactions between the flow of air and the airfoil result in the generation of lift and drag by the airfoil. So these same aerodynamic interactions also create a pitching moment on the airfoil, and for airfoils with positive camber, the pitching moment is negative, meaning the airfoil tends to pitch down. And that's why it's important to have a tail to counter that moment. Now here, the pitching moment is positive when it's pitching up, and that's why in this diagram it shows as a clockwise direction, because it's pitch up. And this is just for reference, but if you put a flow of air here on this airfoil, the pitching moment would actually be going that way, because this is a positively cambered airfoil. Now recall that in order to calculate moments, you need an arbitrary reference point, and the aerodynamic center of an airfoil is an arbitrary point about which the pitching moment remains constant as you change the angle of attack. So as you increase the angle of attack of the airfoil, of course the loads would change as you change the flow of air. But there's this thing where if you were to take the moment about a particular point on an airfoil and calculate it, and then change the angle of attack, and then take that moment again and calculate it from the same spot, and then repeat the same process as you increase the angle of attack or decrease it, you'll see that the moment doesn't really change a lot, and at that particular point. And that's why it's important to take note of that point, and we call it the aerodynamic center. Now for low speed thin airfoils, so basically flat plates, the aerodynamic center is at the quarter chord. And again, remember chord means the distance between the leading edge and the trailing edge, and quarter chord is just a quarter of that from the leading edge. And for low speed thin airfoils, the aerodynamic center is typically at here, the quarter of a distance of the chord. Now, the aerodynamic center is not the same as the center of pressure, and the center of pressure is the location where the vertical forces balance. So try not to confuse the two. The aerodynamic center is strictly the point at which the moment doesn't change as you change the angle of attack, and the center of pressure is just the location where the vertical forces caused by the aerodynamic flow balance. Again, as I explained previously, for symmetric airfoils, they have a pitching moment equal to 0 at the aerodynamic center, and it's because of this the same phenomenon of having the the flow being equal at the top and the bottom at 0 angle of attack, so it wouldn't produce any moment. And it is important to understand the pitching moment of an airfoil if you want to keep your glider from pitching downwards. So if you know the moment of the airfoil, or the pitching moment that it generates on its own, then you will need to design a counter moment that will cause that the net moment to be 0, so that your aircraft doesn't pitch down as it glides. So the act of balancing the moments on your glider, aka to have a 0 net moment, is called trim. And that's the main reason why aircraft have tails. And that's to counter this inherent pitching moment produced by the airfoil. So the three main aerodynamic characteristics of an airfoil that's worth paying attention to are lift, drag, and pitching moment. When looking at airfoil data, it's typical to see these three plots, which show the variation of the lift, drag, and pitching moment at different flight conditions. Now, it's interesting to note that lift, drag, and moment are expressed as non-dimensional coefficients. That's why you see C with a subscript of the corresponding letter, C subscript L, C subscript M, C subscript D. And because they are expressed as non-dimensional, but we won't get into the reason why. What's important is that the general idea remains the same. They depict the behavior of the aerodynamic loads as you change the angle of attack. So here we see how all three change with respect to angle of attack. Here this is called the drag polar, and it's expressed in terms of lift, and it's simply because sometimes it's just easier to see, or more useful to see, the variation of drag with respect to lift instead of angle of attack. But the idea remains the same. It shows how the lift, or rather the drag, changes with different flight conditions. Again, as I explained numerous times, as the airfoil lift changes linearly with respect to the angle of attack until the stall region, in which that linearity disappears, and that's because of flow separation. Now the middle plot is the change in pitching moment with respect to angle of attack, and notice how it's near constant since we are taking our reference point about the quarter chord, or the aerodynamic center for low speed thin airfoil. Now if you were to find the aerodynamic center for an airfoil that's not that case, it wouldn't be the quarter chord, but the behavior would still be the same. You'll see that it's almost near constant. And this region here, again, is because of flow separation, and that's why it begins to break, and it's for the same reason that a lift here starts to act a little funky, and it's because of the flow separation. The third graph, again, is called the drag polar because of its parabolic shape. We normally plot the drag coefficient versus the lift coefficient variation instead of the drag coefficient versus angle of attack variation. So on this graph, the drag is on the horizontal axis, and the lift is represented by the vertical axis, which is usually in a 1-to-1 scale with the vertical axis of the lift curve plot. And the reason for that is because typically these two curves are side by side when you look at plots in literature. And it's so that if you were to find if you knew the angle of attack of the aircraft, then you'll be able to find the lift coefficient. And once you know the lift coefficient, you can go and maybe use a ruler and draw a line straight to the drag polar. And at that point, you draw a line straight down to the horizontal axis. And then from that, you'll be able to know the value of the coefficient of drag. So even though you don't know the angle of attack, or rather it doesn't show the angle of attack here, you can still find it. And again, for the reason why it's depicted this way is that it's just more useful to know the variation of drag as lift changes. Airfoil characteristics like lift, drag, pitching moment are strongly affected by a parameter called the Reynolds number. And it's the Reynolds number is represented by these two letters, RE. And the Reynolds number is just a non-dimensional parameter used to gauge the behavior of a fluid. So in other words, it helps predict flow patterns in different fluid situations. So a low Reynolds number tends to produce orderly flow called laminar flow, and high Reynolds numbers produce turbulent flow, and it's just this chaotic mess of a flow here that you see underneath. Now, typical aircraft wings operate at a Reynolds number of about 1 to 10 million. So there's a large variation in the Reynolds number, but they're important to understand because they affect how an airfoil behaves. So knowing the Reynolds number, in other words, the flow regime at which you're going to fly in, is important because you can't use the airfoil data obtained at one Reynolds number and apply it to an aircraft that'll be flying at a totally different Reynolds number, because at those two Reynolds numbers, the airfoil will effectively behave as if it was a different airfoil compared, when you compare the two. So, and that's because of just how the flow, the quality of the flow is around the airfoil. So that's why Reynolds number is important to know. And it's just a measure, like a quantifying number that helps you gauge, the quality of the flow. So, low Reynolds numbers have more orderly flow, while higher numbers are more chaotic. And as you'll see later, and when we compare different airfoil shapes at different Reynolds numbers, the Reynolds number will greatly affect the drag coefficient of an airfoil. So that's why if you want your glider to fly a little further, knowing the Reynolds number would be helpful. Although you shouldn't try to overanalyze the Reynolds number, because it's hard to measure out in the field, I guess, with what you have. So it's just good to be aware of what that means, why you're given a plot and then you see several lines, instead of one, and it's because that's data obtained at different Reynolds numbers, and that just means data obtained at different flow behaviors. Alright, so here we'll see the effect of the Reynolds number on the airfoil characteristics. Notice how at different Reynolds numbers, the drag characteristics of an airfoil changes drastically. So here you can see the plots for the different Reynolds numbers, and they're represented by different shapes. And you can see that the drag polar is heavily affected. Now, on the other hand, at least in these values, at these values of Reynolds number, the lift isn't really drastically affected as the drag. So, at least from this information, the Reynolds number is important to know because of how the airfoil drag characteristics will be affected. All right, so in this section, we'll get to the more exciting parts, which relates to the airfoil selection for your glider. So I'll be talking about some examples that you can take inspiration from for your glider. It's going to be less theory-based as the previous section, so hopefully this will be more interesting to you. But first, before we get to the examples of the airfoils that I found, we need to talk about some key geometric properties or parameters of an airfoil. So the proper reference axis for an airfoil starts at the leading edge and goes to the trailing edge. Now, it's not obvious where the leading edge point is for most airfoils, so the rule of thumb is that the leading edge point is just the furthest point from the trailing edge point, and it's easier to find where the trailing edge point is because it's just the sharpest point here on the airfoil. So if you were to find the largest distance, that will be where your leading edge is. Now, once you know the leading edge, that will be the point at which you reference all other points. So in other words, that's your origin point. On a Cartesian plane, that will be your 0, 0, where everything is going to be measured from. The chord line is just, again, the straight line from the leading edge to the trailing edge, and is taken to be the horizontal axis line of your Cartesian plane here when you're plotting your airfoil, right? So think of this as like a map, and all your coordinates are based on the horizontal axis as your your chord line is your horizontal axis, and then you just take the location of the leading edge and then just draw a vertical line, and that's your vertical axis. Now, the front of the airfoil is defined by a leading edge radius, and you can see that here. This is the leading edge radius, and that's just defining the, I guess, the bluntness of your airfoil. So a large radius helps, it actually helps air stay attached at higher angles of attack. So sort of the same as why you put a camber on your airfoil. It delays flow separation. So naturally that translates to higher stall angles, which again will allow for more lift at takeoff and landing situations, for example. Now, a small radius is more beneficial for faster aircraft because it produces less drag, because a larger leading edge radius will have a blunter cross section, and that will cause more drag. Now, camber refers to the curvature of an airfoil and allows for the airfoil to generate lift at zero angle of attack on top of the effect of delaying flow separation. Now, camber increases the maximum lift that an airfoil can produce, but at the cost of increasing drag and pitching moment. Now, in terms of geometry, there's something called the mean camber line, which is this line here. And the mean camber line is just the line that's equidistant from the upper and lower surfaces of the airfoil. So if you were to draw like a bunch of lines here that were equidistant and tangent to each surface, and you were to find the midpoint of each line, you will get this mean camber line. Now, the camber of an airfoil, like the actual, I guess I would say, the amount it's curved away from its, I suppose, base shape, and that would be a symmetrical airfoil, is defined by the maximum distance of the mean camber line from the chord. So the greater the distance between your chord line and your mean camber line, the more camber, the more curve your airfoil has. And typically, the camber is measured at the maximum distance. So you have your camber line here, you have your chord line here. The maximum distance between the two happens to be here, and that is the number that you use to define how much camber your airfoil has. And that's expressed in terms of percent chord. And what that means is that you just take the actual distance here and then just divide it by the value of the chord. And the reason you do that is because your distances and your measurement of your airfoil will vary along your wing. So it's more useful to know the proportions of your airfoil, because those will remain constant along the span of your wing if you use the same airfoil along the span of your wing. So in that case, if you use percent chord, even if your chord is different from the root, because typically at the root your chord would be bigger and your chord at the tip will be smaller, if you use percent chord, everything will be in proportion, and in relation to each other, everything will have the same distances, even though your chord is different and everything else is a little bit smaller, let's say, on the tip in comparison to the root. Now, the thickness distribution of an airfoil is just the distance from the upper surface to the lower surface, and is measured by the perpendicular distance from the mean camber line. And what do I mean by that? So you see the camber line here, and it curves, right? So if you were to find the distance between the upper and lower surface such that the line is perpendicular to this mean camber line, that will be your thickness, right, at that particular point. Now, again, the thickness of the airfoil is defined by the maximum thickness. So if you go along this line, you'll find that the maximum thickness occurs here, and that is the number that you use to define the thickness of the airfoil. And again, it's expressed in terms of percent chord for the same reasons why the maximum camber is expressed in terms of percent chord. And another way of referring to the thickness, is the airfoil thickness ratio. You should note that thickness has a direct effect on the skin friction drag of an airfoil. And again, camber affects the lift produced by the airfoil, and the lift-induced drag as well as the aerodynamic pitching moment are affected by the camber of an airfoil. So to rehash, in terms of the camber, it affects the lift-induced drag and the aerodynamic pitching moment, as well as the lift, and the thickness affects or is more relevant towards the skin friction drag. So those are the two parameters and the effects they have on the aerodynamics on this airfoil. All right, on to the more exciting portion of this workshop. We're going to be talking about some examples of airfoils that can be used for the competition. So, what is meant by free flight? Free flight means that the aircraft has no external control. So it has to be designed to be inherently stable in flight. So that means that when the aircraft is disturbed, let's say by a gust, the aircraft will return to stable level flight. So that means that the aircraft has to have some sort of inherent aerodynamic properties that will cause it to return to stable flight. And this is achieved by design. So by the location of your center of gravity, your wing and tail incidence angle, so that just means angle of attack with respect to your fuselage, and rudder settings, so the angle of your rudder if you have one. And the end goal is to achieve the longest flight duration. So the first step in choosing an airfoil is looking at what is already available. So you look at already established designs and you just choose whichever one best suits your needs and the design requirements. And you do this because it's time consuming to develop your own airfoil from scratch. Now, after you've found the airfoil that you think is the most relevant to you, after doing your preliminary testing, you can make changes to your airfoil in accordance to the performance that you want. So you can change its shape, and if you really want to get fancy, you can import your airfoil into a program called Xfoil and simulate its performance. Or you can select an entirely different airfoil. So here's our first example of an airfoil used in free flight competitions. And it's called the A18, and it's designed by Randy Archer for the 1993 F1C World Championship. So it has a percent chord thickness of 7.26 and a percent chord camber of 3.84, and you can see the shape of the airfoil here, as well as I think the pressure distribution of the airfoil. Here is an example of the performance plots of the A18. And again, we've actually seen this data before when I was explaining the concept of Reynolds number. And you can see the variation of the drag polar with respect to different Reynolds numbers, and also the lift plot right here. Now, the data that I'm showing here is from a book, and it's a bit of a lower resolution. So I recommend you visit a site called airfoiltools.com and you just look up the same airfoil and you'll be able to see much clearer pictures of the performance plots for this particular airfoil. Excuse me. And here's another example of a free flight model airfoil, and it's called the MA409, and it's designed by Michael Achterberg, and based on the descriptions of the airfoil, it has a fast climb and good glide endurance, and it has a thickness of 6.69% chord and a camber of 3.33% chord. And here is like a cross section of the airfoil here. And again, some pressure distribution plots. Try not to pay attention to this too much. It's just kind of gives you an idea of the distribution of the pressure along the airfoil. So don't worry too much about that one. And again, here are the performance plots for the MA409 at different Reynolds numbers. And you can see that the drag polar is greatly affected by the Reynolds number, but the lift isn't. Now, I showed you two different airfoils and their performance plots with a bunch of data, and I'm pretty sure you're like, what do they mean? How are they relevant to me? How can I interpret these data? So I'll kind of give you a rundown of the performance of the A18 versus the MA409 in terms of something more relevant to you, in glider performance. So they are similar in shape and in performance, but the MA409 has less camber than the A18, which results in the drag polar of the MA409 being shifted downward compared to the A18 airfoil. So if you were to look at the previous slide and compare the two drag polars, you'll see that the drag polars of the A18 is actually higher than the drag polars of the MA409. So I guess I can draw it here. So the A18's drag polars would be something like this, and in comparison, the MA409's drag polars would be lower, be here. So knowing that, from the drag polars, the MA409 has the lowest zero lift drag, which means drag that is not caused by the lift, then the A18. So what does that mean? That means that the MA409 has excellent climb performance, meaning when it's launched, it can reach higher altitudes, but at the cost of glide performance. So clearly there's a trade-off between the two, between climb performance and glide performance. Right? If you have better climb performance, you have to sacrifice glide performance, and vice versa. A mediocre climb can be offset by an excellent glide. So if you have less camber, your drag polar is shifted downwards. However, or rather, because of that, it has an excellent climb performance. So less camber means better climb performance, but at the trade-off of glide performance. So the A18, on the other hand, has better glide performance than the MA409, but at the cost of climb performance. So when choosing between the two airfoils, you need to consider the duration of climb and glide for your particular situation, because that'll dictate which of these two you'll choose. So for hand-launched gliders, the time to climb is much shorter than the time to glide, relatively speaking. So in this case, if you were to put emphasis to time to glide, you would choose the A18. So you choose the airfoil which will make the most out of the situation that you have. And here's just a 3D render of the A18 airfoil in the form of a wing. The next airfoil that we will be taking a look at is the BE50, and it's designed by Eugene Verbitsky and is a former F1C world champion. So for Verbitsky's design, in terms of the wing, he put emphasis on a high aspect ratio, and again later we'll be talking about what aspect ratio is and why it's important. Thin, under-cambered, low dihedral wing. We'll understand again later what dihedral means. And a long tail boom. So this is his configuration for the championship. And now for this particular airfoil, the percent chord thickness is 7.31 and the percent chord camber is 3.96. And here is a depiction of the BE50. Again, here are the performance plots for the BE50. Here's the drag polar affected by the Reynolds number, and then the lift curve plot. Now, the performance of the BE50 differs significantly from the A18 and MA409. So at mid-range values of lift, the drag is lower than the A18. And over the lift range of about 0.5 to 1, there's a smooth increase in drag, as you can see here. So this type of drag behavior, where the increase is smooth, is indicative of good glide performance and over a broad range of aircraft speeds. So all in all, the BE50, because of the way the drag behaves, it has a good glide endurance. Also, this airfoil is less sensitive to trim changes, which implies that this design has a good static stability. So that means the aircraft will have a tendency to stabilize itself during flight. So that's the BE50. So our next airfoil is the GM15, and it's designed by Gilbert Morris and has a good balance between climb, glide, and total endurance. Now its geometric properties are that it has a percent thickness of 6.70 and a percent camber of 4.76. Excuse me. And what's special about the GM15 is that it's referred to as a flapper airfoil. And you can see that it actually has two configurations right here. So using a flapper airfoil is a good strategy in situations where climb and glide are the primary objectives of your flight. So what exactly is a flapper airfoil? So a flapper airfoil is an airfoil with a plain flap that has a low camber, aka reflexed, during the climb phase, and a high camber, unflapped, during the glide phase. So basically, during the climb phase, the camber is decreased because the airfoil becomes reflexed. So it has a reflexed configuration here, as you can see. And during the climb phase, it has an unflapped configuration, which means that the camber is high and it will look like this. Now, this type of airfoil implies that the wing must be compliant, which means that the wing and by extension the airfoil can elastically deform under certain load conditions. So for this particular airfoil, you have to consider to make the best use out of it, with its reflex capability, you need to think about the material that you're going to use to make this wing and to make full advantage of this airfoil. So this is the performance plot of the GM15 when it's unflapped. So when it has its camber. In this configuration, the unflapped GM15 has a very high potential for lift in comparison to the examples that I talked about earlier. So here we have the performance plots for the reflex configuration of the GM15. So here you can see that there's an apparent change in the drag polar in the reflex configuration. The polar is shifted downward in comparison to the unflapped configuration. So the result of that is that the zero lift drag is reduced. So like the MA409 airfoil, the GM15 in its reflex configuration, when it has minimal camber, it has better climb performance for the same reasons as the MA409 airfoil. And likewise, the GM15 in its unflapped configuration or cambered configuration performs more like the A18, where it has better glide performance. So because the GM15 is able to change its shape depending on the load configuration, or rather the load condition, it's able to make the best of both the advantages of the A18 in its unflapped configuration and take advantage of the better climb performance of the MA409 in its reflex configuration. And here's just a picture of the GM15 and in terms of a wing, and just some depictions of the airflow and the lift distribution along it. And the last airfoil that we'll be talking about is the NACA 6409, and it has a percent thickness of 7.26 and a percent camber of 3.84. And here's the shape of the airfoil. And again, the distribution of the lift. And here is a depiction of the performance plots of the NACA 6409. There's less data for this one in terms of the data taken from the book that I got this from. In terms of performance, it doesn't really talk much about performance. However, there are some advantages to using the NACA 6409 in terms of other factors. So the NACA 6409 is more forgiving to manufacture because the airfoil is the thickest out of all the ones that we talked about so far. And here's a picture of the NACA 6409 in terms of a 3D depiction of it. So it's good to consider your method of manufacturing when selecting your airfoils. So choose the airfoil that best suits the means by which you're going to make it. So for example, the GM15 flapper airfoil may not be the best choice if you're not going to, or rather if you're going to pick a more rigid material for your wing and it's not going to be compliant. So it won't be able to take advantage of the changing configuration of the GM15. In terms of the NACA 6409, it's just easier to cut, I suppose, because it's a lot thicker than the other ones that I've talked about so far. So here is a summary of the parameters of the 5 airfoil examples that we talked about. As you can see here, the NACA 6409 is the thickest out of all of them. So in terms of manufacturing, precision-wise, the NACA 6409 is more forgiving. You can also see the camber of each, and that affects the performance of the airfoil. And another parameter that we haven't seen is the pitching moment about the aerodynamic center. So here you can see that they're negative values, implying that each of these airfoils on their own will cause a negative pitching moment, so they have a tendency to pitch down, right? And from this data, you can compare which one will pitch down the most, which one will pitch down the least, and that will affect the design of your tail, whose purpose is to counter the pitching moment of your wing body. So I guess here from this example, the BE50 has the lowest pitching moment, while the NACA 6409, while thicker and easier to make, has the highest tendency to pitch downwards. And again, here is a picture of a wingtail arrangement. And here is the wing body, and it will have a tendency to pitch downward. And you will have to use a tail at a negative incidence angle, and here you can see a negative incidence angle just means it is below this line here, and that will cause the angle of attack to be negative and have a negative lift. So the lift force will actually be downwards, and that will counter the negative pitching moment caused by the wing itself. So that's the main purpose of the tail right here. And again, canceling out the moment caused by the wing body is called trim. So if you're interested in finding the analytical data for your airfoil, you should visit this website here, airfoiltools.com, and it will give you a plethora of information regarding your airfoil. So this picture here, and as well as the performance plots, which are below. They're actually lower here. And also you'll be able to find the DAT file, or the coordinates file, for that airfoil that you want to use. So if you're planning to CAD your airfoil, it'd be useful to have this DAT file because it contains the coordinates of each important point on your airfoil, and then you can use that to CAD your airfoil. So the next portion of this workshop is going to be talking about the wing geometry and tail geometry. So here we have something called the reference wing, and it's basically the most basic wing geometry used to define its geometric parameters. So the reference wing is a fictitious wing that extends through the fuselage to the aircraft center line. So in a real aircraft, the fuselage would be somewhere here, and this reference wing just extends right into the center line of the aircraft. So that means that the root chord for the reference wing is at the center line of the aircraft and not at the part where the wing connects to the fuse, if your wing is embedded into your fuselage, as most aircraft are. So the reference wing area is the surface area of the wing. So for this reference wing here, the reference area would be this enclosed section. And for the wingspan, so the wingspan is denoted by the letter B, and it extends from tip to tip. So that's your wingspan. And your half wingspan, b over 2, is just the distance between the tip to the root. Now, as you can see, this the chord along the reference wing changes as you move along the span. The chord at the tip is known as the wingtip chord, and the chord at the root is known as the root chord. Chord distance is denoted by lowercase c with the appropriate subscript. And there's something called the mean aerodynamic chord. Now, the mean aerodynamic chord is just a special location on a wing that is some distance from the center line. So let's say here to here, some location. And it's denoted by C bar. Now here in this diagram, there's no bar, but typically there should be. There's a bar here. And why is the mean aerodynamic chord important? Like why do you want to consider the mean aerodynamic chord? So the mean aerodynamic chord, which is located somewhere along the wing, it doesn't have to be here, but here in this depiction, they put it here. It's a special location along the wing where all of the area of the wing seems to be at that chord. So what does that mean? So for example, at the mean aerodynamic chord, the whole wing has its aerodynamic center, like this entire wing, at about the same location as the airfoil located at the mean aerodynamic chord. So here. So if you were to find the pitching moment of the airfoil at the mean aerodynamic chord, you actually find the pitching moment of the entire wing, not just at that specific cross section. So here they sort of superimpose the mean aerodynamic chord here. And, oh, sorry, I guess so this is I just noticed, this is just some local chord here. But let's assume that it is the mean aerodynamic chord. And although it's a little bit offset here, let's superimpose it on the root chord, right? So now, knowing the mean aerodynamic chord and its location, as well as the location of the aerodynamic center at that point, you can model the wing as if it was just this one line here. So that means the aerodynamic center of the mean aerodynamic chord would be somewhere here. And if you know that location with respect to the center of gravity, you have your pitching moment of the whole wing, right? And once you have that information, you can now calculate the size of your tail and the boom to be able to counter that pitching moment to trim your aircraft. So that's why it's important to know the mean aerodynamic chord. And another geometric property here that's shown is the sweep angle, and it's depicted or denoted by the letter uppercase lambda, I believe. And that's just measuring how much sweep your wing has. Now, if you're determined to find where the mean aerodynamic chord is, here's a diagram showing the location of the mean aerodynamic chord, and you can find it using this formula here, where lowercase lambda just means taper ratio. And taper ratio is just a ratio between tip chord and root chord. So tip over root. Bear with me. So that's just lambda taper ratio. And in the previous slide, I talked about the sweep angle. That was with respect to the leading edge. But if you were to find the quarter chord point for each cross section here along the wing, so it'll kind of look like that. And if you were to find the sweep angle with respect to that line, that would be your quarter chord sweep angle. And that parameter is more relevant, I guess, for subsonic flights like gliders, as opposed to the angle, the sweep angle for the leading edge, which is more relevant to supersonic flight. So if you want to put a sweep on your wing, you'd want to pay attention to this line as opposed to your leading edge. Okay, so in this section we'll be talking about aspect ratio, and I've been mentioning this term several times earlier in this workshop, and now we're going to define what that actually means. So long skinny wings are referred to as high aspect ratio wings, and they have less drag than short wide wings, which are referred to as low aspect ratio wings. And you can see that typical gliders have high aspect ratio wings. Now, in nature, birds with long wings can glide with less effort, such as here, while birds with short wings have greater maneuverability, but have to work harder to fly. So like hummingbirds, they have to constantly flap their wings, but they're much more maneuverable than, let's say, an albatross or a seagull. So here you can see that. Now the aspect ratio of a wing is defined as the span of the wing, B, divided by the chord, and that's for a rectangular wing. Now most wings have a taper, as you can see for this one. So to get around that, aspect ratio can be calculated using this formula instead, which returns the same units. So instead of just the wingspan, B, you can use the square of the wingspan, B squared, divided by the wing area, A. And that gives you the aspect ratio of the wing as well. Now, why is it important to consider aspect ratio? Aspect ratio is important because 3D wings tend to form things called vortices. Now recall that at the top of the wing, or an airfoil, the air has lower than ambient pressure, while the bottom of the wing or airfoil has higher than ambient pressure. Now for a 3D wing, air at the tip tends to escape from the higher pressure region to the lower pressure region, and it forms this sort of circular arc. Now what this means is that this higher pressure air is going to occupy a region at the tip here, at the upper surface of the tip, of lower pressure air, right? So the total air pressure actually increases here at the top surface because this higher pressure air is leaking into the lower pressure region. Now, because we're talking about how lift is produced by a difference in pressure, in ambient pressure here, because this higher pressure air is leaking into this region, the pressure difference between this region now in comparison to the ambient pressure is now lower. So that means that the lift produced at the tips, because the pressure difference is lower, is reduced. And again, in addition to that reduction in pressure difference, the leaking of air causes a circular stirring motion that leads to the formation of these things called trailing vortices right here. Now, this stirring motion actually affects the flow of air around the airfoil, and the oncoming air seen by the airfoil is also affected, and it causes it to be pushed downward here. So this is the original oncoming air, and because of the stirring motion, it causes something called a downwash, and it pushes the airflow downwards. And what that translates to is that the airfoil sees a lower angle of attack. And again, remember from before, angle of attack affects the lift generated by the airfoil. And if the effective angle of attack is lowered, as seen by the airfoil, because of this downwash, the lift generated would be lower than what it would have been. And also, after that, reducing the lift due to the decrease in pressure difference and due to the decrease in effective angle of attack, the trailing vortices actually produce drag. And in terms of aerodynamic theory, that drag is referred to as drag due to lift. So this formation of vortices at the tip, because of the leaking of the air, needs to be alleviated. And you can do that by having a higher aspect ratio wing. Because higher aspect ratio wings, the span is much larger, and that means that the wings are going, or rather the wingtips are going to be further from the majority of the wing area. And that means that the effects of this vortices forming at the tip of the wing will be less than, let's say, a lower aspect ratio wing where the tips are closer to the rest of the area of the wing. So that's why it's important to have, to understand the advantages of having a higher aspect ratio. And it's because it's sort of separating further the effects of this formation of vortices away from the rest of the wing. So again, wing with a high aspect ratio has tips further apart than a wing with an equal area with a low aspect ratio. So that means that the amount of the wing affected by the tip vortex is less for the high aspect ratio wing than for a low aspect ratio wing. That translates to the strength of the tip vortex being reduced for the high aspect ratio wing. So a high aspect ratio wing does not experience as much loss of lift and an increase in drag due to the tip effects in comparison to a low aspect ratio wing. And you can see that here in this graph, where a lower aspect ratio wing has a lower slope, and that means at the same angles of attack, its potential to generate lift is much lower than the wings with the higher aspect ratio. And that's because the tips of this wing, let's say, is affecting more of the wing compared to the tips of this wing. And another effect of aspect ratio is the change in stalling angle. So a lower aspect ratio wing will stall at a higher angle of attack than a higher aspect ratio wing, and that's because of the effective angle of attack seen by the wing, right? So in a way, because it's seeing a lower angle of attack than it should, then it'll take a higher angle of attack for it to stall, and vice versa for higher angle of higher aspect ratio wings. It will tend to stall much sooner, or rather it'll stall at angles of attack that it will actually stall at in comparison to this one here. So here we'll again talk about taper ratio, and as I mentioned previously, taper ratio is simply just the ratio between the tip chord and the root chord, and here's the formula for that. In this case, because this is a wing attached to a fuselage, they defined it as the root being the chord at which the wing meets the fuse. But if you're using a reference wing, it'll just be the center line of the reference wing that you'll use as the root chord. So it really depends on the situation that you have. So why is taper ratio important? Well, in simple terms, and I won't go into the details as to why, it's just good to know that the taper ratio will affect the lift distribution along the wing. So the lift distribution is just pretend that each section of this wing here is an airfoil, and they all produce a certain amount of lift. And as the airfoil changes in size and potentially in shape as well, the lift generated by that section will also change. So to get the most efficient lift distribution along the wing, you have to have something called an elliptical distribution, and it's seen here by this green plot here, this green distribution. So if you want to try and get a wing to have this more efficient shape of lift distribution, if you have a rectangular wing, a taper ratio of about 0.45 will produce a lift distribution that's very close to this shape here. And that just means, in simple terms, you're going to have the most efficient lift distribution. So next we'll be talking about wing incidence. And the wing incidence angle is just the pitch angle of the wing with respect to the fuselage. So here in this diagram, they drew their line here, their longitudinal line here, and that's their reference line, and here is the angle of incidence with respect to the chord of the wing. Now, wing incidence angle is chosen to minimize the drag from the fuse at some flight condition. So the wing incidence angle is just the ideal angle at which the wing is with respect to the fuse, so that the fuse produces either less drag or actually in some cases it'll even produce lift in addition to the wing. So it's just some parameter that you can just play around with to make the most out of the shape of your fuse, or just the aerodynamic properties of your fuse, while at the same time having maximum aerodynamic performance of your wing here. So nothing too overcomplicated, it's just something to be aware of, the wing incidence angle. Now here's another important, I suppose, concept, and it's called wing dihedral. And wing dihedral is just the angle of the wing with respect to the horizontal when seen from the front, as you can see here. And A positive dihedral means just the tips are higher with respect to the horizontal here. And what that does is that it tends to roll the aircraft back to level flight. So when an aircraft with a dihedral is disturbed from level flight, like here, the aerodynamics of the dihedral will cause a restorative rolling moment that will bring the aircraft back to level flight. And that's just the positive consequence of having a dihedral. I won't get into the specifics of why this is the case because it gets a little bit complicated at this level, but it's just something that is a good design feature to have, a dihedral, and it's just for that reason where an aircraft will get disturbed, and when it's disturbed and it keeps flying, because the dihedral will cause it to go back, go back to steady level flight. Now, there is something as a too much dihedral, and that produces an effect called Dutch roll, Dutch roll, which is something that I'll talk about in the next slide. So if you have too much wing dihedral, too much positive dihedral, you'll end up with this thing called Dutch roll, where if your aircraft again is disturbed, it will try to stabilize itself, but the rolling moment that is produced from when the aircraft tries to stabilize itself will be too much. So instead of just being returned to steady level flight, it'll be in this perpetual motion where it's trying to stabilize itself, and that's what Dutch roll is. So it'll just be a feedback loop of it trying to stabilize itself, and it never returns to a stable flight or level flight. And in your future courses, this phenomenon is associated with dynamic instability, whereas the previous slide is more static stability. Now, another thing you can do as an alternative from a dihedral is to have a high wing arrangement. So this has to do with the vertical location of your wing with respect to the fuselage. So if you want to have the same effect as having a dihedral, a positive dihedral, you can have your wing here above your fuselage, and that will have the same effect as if you had a dihedral, where if the aircraft is disturbed, a stabilizing roll moment will be caused by this arrangement to put it back to level flight. Now, a wing with a low wing arrangement with no dihedral will have the opposite effect. So that's why it's typical that you have a dihedral for low wing arrangements. So now we'll be talking about wingtip geometry, and the geometry of your wingtip is basically addressing the same issue as your changing of the aspect ratio, and it has to do with minimizing the effect of the wingtip vortices. So if you have a wing with a rounded wingtip, it actually makes it easier for the airflow to flow upward, which increases the formation of the vortices that I explained earlier. Now, a wingtip with a sharp edge actually makes it more difficult for the air to escape from the bottom to the top. And likewise, a simple cutoff tip offers better performance than the rounded wingtip for the same reasons as the sharp tip, where the air has there's more resistance for the air to flow from the bottom to the top. Now, a drooped or an upswept wingtip tries to trap the airflow using a curved surface. So let's say for here, for a droop wingtip, the higher than ambient pressure air at the lower surface would have a harder time escaping towards this direction here because of the droop tip. And likewise, for an upswept tip, the air would flow somewhere else as opposed to trying to get to here in this section. And now we are at the final section of this workshop, tail geometry and arrangement. So here's a diagram of basically the effects of trimming an aircraft using the tail. So tails are designed to operate at only a fraction of its lift potential. So that means that its incidence angle is not at the near stall, right? So it doesn't generate almost maximum lift. So it'll be lower down its lift curve line. So here, I guess I'll draw it. So let's say this is the lift curve of the tail. You don't want the tail's angle of attack / angle of incidence to be here, because a change in that would cause it to stall, and then you lose the effect of your tail counter moment to the wing fuselage body. So typically your wing incidence angle should be around here, so you have some allowance, right? So your tail doesn't stall, and that's why that's what I mean by tails being designed to operate at only a fraction of its lift potential. So tails provide an aircraft trim, stability, and control. And again, trim refers to the generation of a lift force that by acting through some tail moment arm, so here, about the center of gravity, balances the pitching moment produced by the wing body, which I explained earlier in this workshop. So an aft horizontal tail typically has a negative incidence angle for that reason that I explained earlier, which will produce a downward lift force to balance the wing body pitching moment. So actually, if I were to draw this, the lift, since the angle of attack / incidence angle would be negative, so here it will actually be a negative value. And again, there's actually a mirror here where this is the stall region. So, and that's just for the reason that we want to have a negative lift so that the direction of the lift is down, and it counters the, let's get a better color here, negative pitching moment about here, caused by the wing body / wing fuselage arrangement. Likewise, the vertical tail surface fulfills the same role essentially, but in the yaw direction instead of the pitch direction. Although most aircraft are symmetrical, thus in normal flight, unbalanced aerodynamic yawing moments aren't really as prominent as this pitching moment here. But it's still there for stability purposes and countering moments in the case that there is a moment in the yaw direction. So overall, the tail of an aircraft provides an element of stability that restores the aircraft from an upset pitch or yaw. And that's pretty much the main function of a wing, or rather, sorry, a tail. Now, there are many tail arrangements that can be used for aircraft. The most typical one is called the conventional tail arrangement, and you can see it here, where the horizontal tail surface is located here, and the vertical tail surface is just here. And the conventional tail surface provides adequate stability and control, but at the lightest weight, because there's less reinforcement required in the structure, because the connection, or rather the hard points here for each surface is sufficient in securing the tail surfaces and doesn't need additional reinforcement. So therefore there's lighter weight. Now the T-tail is also widely used, but it's heavier than the conventional tail. But it allows for a smaller vertical tail and keeps the horizontal tail surface away from the wake of the wing. So because the horizontal tail surface is higher here in compared to here, the wing, which is usually located along this line here, the airflow that comes from the wing is usually disturbed. So by moving the horizontal tail surface higher, the airflow that is seen by this surface is much cleaner than it would be for, let's say, this configuration here. Now, the cruciform arrangement is a compromise between the conventional arrangement and the T-tail arrangement. And here, the H-tail puts emphasis on the vertical tail surfaces, sort of like here, where the T-tail puts emphasis on the horizontal tail surfaces. So by positioning the vertical tails and I guess splitting them up, the surface here, so they have the same effect, a stabilizing effect, you're moving them away from, again, the disturbed airflow from the wing. And a more exotic tail arrangement is the V-tail. And it offers less interference drag and also reduces the wetted area of the tail. And wetted area is just the exposed area to the airflow. And so the aerodynamics of this is basically going to have to be the same as this, except that you sort of divide the function of a vertical tail and a horizontal tail between these two surfaces. So this one surface is acting as a hybrid, and it fulfills the same role simultaneously as a horizontal surface and a vertical surface, and likewise for this one here. So the aerodynamics of a V-tail is a little bit more complicated because for a conventional tail, you can easily separate the function of pitch stability and yaw stability, whereas for these two, they're basically integrated. So one is affecting the other more directly because they share the same surface for two different stability purposes, if that makes sense. And that concludes the RUAT Aerodynamics workshop. And here are the following sources that I used to make this workshop. The main reference here is Raymer's Aircraft Design, a conceptual approach to aircraft design. And most of the theory comes from this book, in addition to some sections on stability from Nelson. And the data on the airfoil examples that I talked about are from this book, if you're interested in reading up on more about them. It's called Summary of Low-Speed Airfoil Data. In addition to this video here by the Science of Flight team, where they also talk about the same airfoils for their glider project. And the link to that video is here. So these are my primary sources for making this tutorial. And if you want to look into more information about what I talked about here, feel free to check out these references